Jackie, thanks a lot for introduction. Thanks a lot for inviting me. I think this is a super exciting and timely topic, right? We really, as the robotics and learning community, really need to think how we can do benchmarking in robotics. And I'm going to talk kind of coming from a perspective where I fully appreciate, I think, kind of the power and need for deep learning, reinforcement learning for robotics to make progress there. At the same time, I also come from a robotics background where I'm someone who really cares about getting things to work on real robots. And also recently have looked more and more into simulation. And so today I'll talk about how we can maybe leverage simulation to do more benchmarking in robotics for manipulation tasks. That's what I'm going to focus on. First, some high-level statements. I hope these are not I don't know, overly controversial. We'll see about that. But I think benchmark is just crucial to drive progress in robotics, right? We need to be able to measure how we're doing. I think there's too much work going on in robotics where we just show a little demo at the end of a paper, little experiments, and then try to make very general claims about the capabilities of our techniques. And I think we can clearly learn there from other communities. At the same time, of course, we also all agree that robotics benchmarking is not quite so easy. So it's not just a static data set on which you can do classification, just because robots are in this interactive setting where they have to physically interact with the environment. And also, we have to be very careful that we design benchmarks such that in light, for example, of deep learning, that they don't lend themselves to easy overfitting to the things that we actually want to measure. On the one hand side, I feel benchmarking on real robot hardware is just very, very hard. There's a huge amount of effort that has to go into this, and I'm sure there's others maybe later in the panel or in the meeting who might not agree with this, but I think it's just very hard to do thorough benchmarking on real hardware because we need to scale it to many different tasks. It's very expensive. Not many kind of teams can, for example, afford to host, for example, let's say a benchmarking system that others can use. And not many research labs can also just afford setting up these benchmarking environments in their own environments. That's why I think kind of a very viable and important way moving forward is looking at simulation, physics-based interactive simulation for benchmarking, where the advantages are, of course, that by having full control over the environment and all the, let's say, almost all of the randomness of these simulators and the scenarios we are setting up, we can really generate kind of the scenarios in which we can do reproducible results, reproducible kind of experimentation and compare things against each other. Of course, since it's in simulation, it's pretty easy to scale, to test in many scenarios. Another advantage is, of course, also that ground truth information in simulated environment is typically inherently available up to a certain level, depends on what you care about. But we can also use this ground truth information, for example, to generate training data, thinking about machine learning, and also then later to evaluate different techniques. Of course, one big open question is, where do we generate all these assets and tasks that are precise enough so that we can actually do the benchmarking in them? That's an open questions. And also, of course, many tasks that we actually care about, we just can't simulate at this point at sufficient accuracy so that they lend themselves easily for benchmarking. So there's limitations to that, but again, at the same time, I believe that that it's a very promising direction, at least. So here, just quick overview of some of these ongoing or past benchmarking environments and attempts. So there's, on the one hand side, benchmarking on real robot systems. There's one that's very well known is, for example, the NIST benchmarks, where they came up with these task boards down here on the left. And these are often then combined with, I think, competitions that typically run at the IROS conference. That's a very well-known benchmarking system. Also, another recent attempt, for example, the tri-finger system is where it's really about benchmarking RL control policies on a real system where people can then just submit their code and it's running on the hardware, which means you can benchmark techniques on a real hardware, but you don't need to maintain the hardware and things like that. There have been other attempts out there doing this. I think one high-level observation is really that it's very hard to convince many people to adopt these benchmarks, simply because if it requires you setting them up in your own environment, then often the burden is just too high. Also, if the benchmark is kind of phrased like a competition at a conference, then also the effort that has to go into it is just extremely high, and many people just are not going to do that, to be honest. Setting up environments like, for example, the tri-finger system or what the OCR TOC system is, where they also provide like benchmarking in the real world. I think it's just a tremendous amount of effort that has to go to host these kind of systems, right? So that others can log in. And it's also not easy to adapt these tasks to new settings and things like that. So there's various caveats if you want to do benchmarking on real robot systems. Now, of course, this being at CoRL, we're all aware of a lot of the benchmarks going on in the what we call embodied AI environments, 3D simulated environments that especially also were driven a lot by the computer vision community. So what's great about is that they are fully interactive 3D simulated environments in which you can train your agents and test them. They have many different tasks. There's a lot of focus also on, for example, visual navigation, higher level planning, and reasoning for manipulation. So the focus here is more on, I would say, visual longer term reasoning rather than low level, let's say, physical interaction. Many of the physical interactions, like really manipulating these things such that it transfers to the real world, is often really abstracted away in these kind of environments. There's other environments that are a bit more focused on the lower level control side. These were developed, I think, mainly also for deep reinforcement learning, testing deep reinforcement learning algorithms. Many of them focus on manipulation skills. I think these are much closer to being actually realistic. So there's really kind of often low-level control involved. There's been good success on transferring results from these environments for locomotion kind of tasks. I think for manipulation, there hasn't been that much effort really showing that if you do well in these environments, that it immediately just transfers to the real world. I think the most recent effort in this domain I like also is House's the many-skill environment here on the lower left that are becoming more and more realistic. At the same time, some of these environments, I think we have to be careful how they are set up. So what we've often observed is, for example, that let's say the camera position, for instance, between train and test set are identical, and the environment is, or the background of the environment is sometimes more or less identical, which of course lends itself really well to overfitting if you have a deep reinforcement learning system. So I think we just need to be careful with these environments to make sure that they have the kind of variability that prevent them from overfitting, so that we can hope that these results really transfer to the real world. I want to talk about some examples, not fully fledged benchmarking examples, but just some areas where I think simulation has been shown to be hopefully sufficiently good that we might be able to transfer these results to the real world. This is, again, more about low-level simulation tasks. Compared to the embodied AI tasks, it's kind of, some people might say these are kind of the boring stuff, right? Like about picking up a rigid object. Many people might think that's not really interesting nowadays anymore. But as a roboticist, I must say, if we could solve all these so-called boring tasks, I think it would be really amazing. if we had robots that can really do these things really well in the real world. Okay, so I'm going to talk briefly about like grasping of rigid object, motion generation, and then object rearrangement and context-rich industrial tasks. So on benchmarking grasping, this is work especially Clemens and Aditya and Arsalan drove forward, which is using physics simulation for grasping objects. So what they did here was they took, for example, the ShapeNet dataset, almost 9,000 objects from the ShapeNet dataset, as you can see here on the right. And for each object, they tried many, many different random grasps and then fed them, as you can see here on the left, through a physics simulator and use physics simulation in order to figure out whether these grasps are stable or not, meaning that if you move the gripper, whether the object stays within the gripper. So what you can then generate is here, as you see on the right, a data set of objects, and each object is annotated with 2,000 grasps that were deemed to be successful, stable grasp for these objects. Okay. You can use this data set, of course, we've shown that, and I'll give just one brief example for training a grasp system. But I think you can also use this kind of as a first attempt towards benchmarking, where, for example, if you want to benchmark your own technique on that data set, you can, for example, compare the distribution of grasp that your system generates to the distribution of grasp that comes from that annotation. The big assumption here is that if you have a grasp to which there is no nearby grasp in the data set, then it's kind of assumed not to be a successful grasp, right? So we're kind of assuming that these 2,000 grasps kind of cover the whole space of possible grasps of these objects, which is some kind of limitation. And ultimately, I think if we really want to fully benchmark grasping, then we need to do this actually with the physics simulation in the loop, which means you submit a grasp proposal on an object, and then we need to run that through the physics simulator in order to do this. We haven't done that as a service for benchmarking, but I think this would be a next step in order to make this even more powerful. Here's just one example that kind of shows that if you use this data set, this was work that Arsalan did with the grasp network a while ago, that the fact that when you train a deep network on point clouds that are rendered from this data set with grasps, that they actually have a pretty high success rate in the real world, which means somehow that the data set itself has a pretty high quality, I think, with respect to sim-to-real transfer. And I think that is something that we, of course, as roboticists always should care about a lot. Okay. Another area that I think is very important, and I'm really looking forward to Lydia later on sharing her thoughts on this and her progress in that domain, is benchmarking motion generation for manipulation. It's one of the very well-known classical problems for robot manipulation, where you say you have, let's say, a current configuration of the robot, you have an environment that is obstacles, and you have a goal position. The goal position of the robot could be either given in workspace where the gripper should move, but it could also be a goal represented in configuration space. And now you want to generate a path so that the robot gets to that goal position while avoiding collisions with obstacles. And that's, again, it's a big research community that's been working on that for a while. And it's interesting. So we came to this because we realized that, first of all, there are no perfect solutions to this problem out there yet, I would say. But also, it is extremely difficult for someone going into this area to find out which of the existing techniques are actually the ones that you should use in your practical application domain. Because often papers are written where people come up with their own little benchmark system, and then they show experiments where, of course, their technique does better than other techniques. But even though this domain seems very suitable for benchmarking, there has been very little success in, I think, on developing benchmarks that are kind of relevant for real-world applications that we as practitioners might care about, that cover a wide range of kind of scenarios actually. There's been some recent work, especially by Lydia Kavrakis' lab, going on Motion Benchmaker, where they developed a system where you can set up different environments for different robot platforms and come up with your own kind of motion planning benchmarking system. The limitations of the time when the paper came out is that I think the variability of these environments isn't that large yet. They also don't really provide a full evaluation protocol, which of course should come with a benchmarking system. And often what is done by the motion planning community is also that they assume, for example, that you have perfect knowledge of the collision and all the objects in the scene, whereas in a realistic setting, you would maybe like to be able to benchmark a system that only uses point cloud observations or something like that, right? So I think there's still work to be done, but there's a little bit of progress at least going on with Lydia's work. Just also as a little bit of a plug for the work that Adam is going to present here at CoRL and that kind of motivated us to go into this area and to observe the limitations of the benchmarking in this motion generation area is what we thought. We do a project as follows, where we say, well, we're just going to simulate many different environments. And for these environments, we're then going to use an off-the-shelf motion generation system in simulation, and then do behavior cloning to learn a policy that can replicate this behavior. And by doing that, we just realized again that there is no existing technique out there that just solves these problems, even in simulation, extremely well. But where we are now, you should talk to Adam through a very painful process and long runs on a cluster, is we now generated a data set of these kinds of environments where we procedurally generate the environments and set goal and configurations of the gripper, and then generate more than 3 million demonstrations of how the robot should move between two locations. And then we were able to train a deep network, motion policy networks, MPI-nets, that can take in a point cloud, not perfect collision information, but a point cloud of the environment, and then map that in real time to a motion policy. So you can see here on the right are two examples of these MPI-nets now operating in the real world. So, and this data set will be shared with the community and people can use it. It also comes then with evaluation protocols where we provide the functions for doing collision checkings and all of that to make sure that if you want to test your algorithm, that it doesn't generate collisions and things like that with the environment. Interestingly, just briefly also, just to highlight the need for benchmarking, the process of writing and publishing this paper was pretty painful because we got feedback from reviewers that was very, very inconsistent, right? We actually tested this system also on the benchmaker environment developed by Lydia Kavrakis' lab. And despite that, despite doing all of this, there were results where one reviewer said, oh, this is amazing. I love that you tested it in all these different environments. And someone else just said, oh, I think these tests are way too easy and it's all too simple and I have no idea how this generalizes, right? So I think we just need to keep on working on developing benchmark systems, even for tasks like that, that are kind of accepted by the community as something that if you do really well on these, then that should be something that also works pretty well in the real world. Expanding from just motion generation more to object rearrangement. This is a recent work that Aditya has done, is kind of scene generation. On the left, you see different kind of scenes we can generate procedurally. We can populate them with objects. We can do collision checking in these environments. And you can see that then in these environments, we also can generate rearrangement tasks where you should pick up a certain object, grasp it, move it out of the shelf, for example, and put it at a different location. So, and then the technical details here don't matter, but then, of course, Aditya was able to train a deep network system that is able to do very well on that training data. But that system on the left, we will also publish as a benchmarking environment that people can then use for their own research. So I think this whole space of rearrangement planning is also something where I believe we can do pretty well for benchmarking. Here's now just an example that this then actually translates to success in the real world using point cloud observations. One final example is benchmarking industrial kind of manipulation tasks. This is one of these NIST task boards. The problem with this is, again, it's really hard to do this in the real world. So we thought we would want to do this in simulation. It turns out simulating this is very, very hard and very, very slow because you have these really context-rich environments. So because in the NVIDIA lab, Yash, he worked with our simulation experts to come up with a simulation system that can now do these context-rich simulations very fast. So here we can, for example, see we can now simulate 1,000 nut and bolt kind of interactions in real time. And this was before that was not even able. The fastest before that time was actually doing a single nut and bolt at 1/30th of real time. We can now use this to start training reinforcement learning policies in this. And again, we now also published kind of different environments in which people can evaluate and test their reinforcement learning algorithms. So far, our training has been done on state information, which of course does not immediately transfer to the real world. So we're looking into adding touch information as well, so that we can train policies that use touch feedback as well. With that, I want to come to the conclusions. So I think there's been really excellent work on these 3D embodied simulation environments that people can use for both training and benchmarking. A lot of that has been done outside of, let's say, the core robotics community because it serves so well the learning aspects. Sometimes you might say that maybe we're getting almost kind of too many of them because it might be too easy to set them up in simulation. I think what we need is a bit more benchmarking efforts on these kind of low-level mundane aspects of how to actually control a robot in the real world, like some of the examples I showed you. I think simulation is, of course, a really promising way to move forward with this. There's several caveats, of course. I think we can do this pretty well for object grasping, rearrangement, motion generation, and these context-rich simulation. We need to make sure that if we set up these benchmarks, that there's enough variety in the tasks, in the assets, in the environment, so that we avoid overfitting, and so that the system can hopefully transfer to the real world. For benchmarking, we need to make sure that even on the test side, simulation should be in the loop itself, so not just labeling, but simulation. And we need to also make sure that this perception is somewhat realistic. I think what would be good is if there was maybe something like a sim-to-real certificate for benchmark environments, where if you train your system on a benchmark, if there was some notion of how well will the results that you achieve in this environment transfer to the real world. It could be at two levels, where at the one hand side, you could say, if my system does well on this benchmark, then I know that it does well in the real world. Another certificate could be relative, where I say, if my algorithm does better than algorithm B in this benchmark, then I can pretty sure that my algorithm will also do better in the real world than algorithm B, right? So I think we have to think about how to make sure that, again, sim to real is taken into account there. And of course, there's many limitations on simulation, and benchmarking those with the full physics simulation is gonna be hard, but I think it's not impossible. And again, the alternatives are very difficult here. And with that, I'll thank you. Should I stop sharing for Q&A?
Thank you very much, Dieter. We have a couple minutes for questions. If anyone has a question. Yeah, Abhinav?
Yeah, thanks, Dieter, for the great talk.
I'll repeat it.
Okay.
Yeah, Abhinav says thank you for the great talk.
Thank you.
If there was no issue with the engineering of a real robot benchmark, and if there was no issue with like sharedness of a real robot benchmark, does Dieter believe as a roboticist, a real robot benchmark is always better than a simulated benchmark?
Okay, so tell me if I summarize it incorrectly, but Abhinav is asking if there's no issue with the simulation, like if it's oh, I see. If there's no issue with the engineering for a real robot, do you still think that or do you think that a real robot benchmark would be better than a simulation benchmark? Is that okay? You say it.
Dieter, I'm coming here so that you can.
Hey, Abhinav.
Yeah. So my question is actually very simple. If there was no constraint on engineering, let's say magically we have thousands of engineers and we have no constraints on building a shared resource like money-wise and so on. As a roboticist, do you believe a real robot benchmark will always be better than a simulated benchmark? A very simple question. BC, I think you got it now. Yes.
And of course, you know that wasn't a simple question. Do I believe that? No, actually not quite. So first of all, of course, again, I think it's going to be really important for us to always stay connected to the real robot stuff, right? And make sure that if we do sim benchmarks, that they are connected to real world results, let's say, right? I think there's still advantages, even if we could do it all in the real world, which I just don't believe, because simulating, it's not just a simple benchmarking environment you can set up, right? You need to benchmark many different kinds of environments. So you have to physically set up all these environments and things like that. I think it's going to be extremely hard to thoroughly investigate that. At the same time, I think benchmarking in sim has the advantage that you can do it very quickly, right? You can run maybe 1,000 times real time and scale there to a much larger community that can benchmark their stuff at the same time, and you don't need to share the hardware across all of these efforts.
I mean, I understand that.
I lost my job.
I understand the argument that building new scenes every day in a physical world is hard. I mean, we can debate about it, and I will in my presentation argue against it. But I think what I'm not totally against is like, why do you need speed in a benchmarking? Like you are saying, oh, it could be super real time and so on. I'm not talking about training. I'm talking about benchmarking. In benchmarking, you're just testing in a few environments and so on. So I do agree that simulation has one advantage, which I cannot get in the real world, is the super fast speed. If you have to do thousands of like 1,000 times real world and so on, which you can do by maybe having 1,000 robots in the real world and so on. But assuming that is still, I mean, I'm just trying to understand, is there a real reason why you need 1,000 times faster in benchmarking?
Yeah, no, you're of course right in that respect. I think the risk, let's assume you want to benchmark rearrangement in kitchen environments, right? Simple thing, kind of the rigid object manipulation stuff, rearrangement in a kitchen, and you want to benchmark that in the real world. Now you set up a kitchen in which we can do this. And of course, we all know that what's going to happen is people are going to overfit to that physical instance of the kitchen on which you're benchmarking, right? Now you can hide that kitchen and things like that, but there will always be some overfitting. So in order to avoid that, you need to set up a sufficient number of kitchens that cover sufficient variety so that people can't overfit to it, right? And I think doing this, given the complexity of the whole setup in the real world, is just going to be extremely difficult.